So, welcome everyone. We are going to consider the following topics, and you're going to see them in just a moment. Let me test it. Everything is working? Okay. So, we are going to look at, just a moment. Let me check. It seems it works. So, this is lecture number 15, and we are going to review, before we continue with our considerations, we're going to review, this is from last week, sample moments of processes. I'm going to do that quick. So there is basically a sample of a stochastic process, whatever it could be. So the sample size is T. This is basically what you have, capital T. And then the sample mean is, of course, the sum of the observations divided by the number of observations. And the number of observations is, of course, capital T. So you might basically be aware of that. Now, the sample variance is written like this, okay? So basically, 0 stands for the time lag. Okay, so there is no time lag basically with respect to the second part. This is 1 by capital T times the sum of the squared deviations from each observation to the sample mean. Okay, this is also mean of the squares minus the square of the mean of a sample. I saw basically in previous assignments that some of you guys were applying this not in a context of the simple linear regression because they were correcting the variance, but the correct variance does not minimize the residual sum of squares. So that was one basic point which I was basically criticizing, but they came back to the slope and the coefficient and whatever. So, but if you just remind you guys, and that is something that I saw, this is a pattern. If you apply a statistical software, which you can, by the way, so you don't need to, do the things that I basically would consider using your hands. But if you apply a statistical software, you should exactly know what it's doing. Okay, so if you're supposed to calculate empirical variance, and empirical variance only, which means basically the uncorrected version, then you're not supposed to basically perform corrections with degrees of freedom. If you do, then I would basically, penalize you for that. So that's one of the reasons why your assignment might not be having the result that you might expecting. Okay, so just for that. Okay, now the sample autocovariance is going to be basically, and I want you to remind you on that. This is also divided by 1 by T, by the way, although it has T minus H summands. Although it has T minus H summands, it is divided by T. You can do that differently, of course. There is different versions of that, but I would like to remind you on that one. And the reason for that is, of course, because if you calculate the sample autocorrelation, you simply divide the sample autocovariance by the sample variance. So that means that 1 by T will be basically, dismissed. Okay, so that will be simply just the sum of the square deviations of the sample YT and of the sample YT plus H. But keep in mind there is just T minus H summands that are involved in the sum because the effective number of observations is going to be capital T minus H. So I like the term effective number of observations. This is the number of observation pairs that you have for the sample autocovariance, guys. Okay? So when you calculate the sample autocorrelation with respect to time lag H, then this is what it's going to be. So you no longer will have basically 1 by T that is involved, okay? And that's something that you would need to understand here. So that is from the practical perspective. Again, you need to standardize this approach somehow. And of course, you could do it differently, but then you might have basically the sample sizes involved, and which is not the case though, okay? So this is how the sample autocorrelation works, okay? Again, so that's just basically the sums that are involved. And I want to basically mention that one also. So let's say you have sample autocorrelations for noises. And that is quite difficult because the number of noises that you have, for example, in AR regression, okay, is not corresponding to the sample size of the time series, guys. So capital T in this case though, okay, is, and again, when you calculate residuals, is not necessarily equal to the sample size of the time series that is involved, because you need to have a model that you would basically consider to estimate the noises. Keep in mind that the noises are not observable in general. Okay, so nobody knows basically what the noises are when it comes to regression models. You would need to estimate them, and the residuals are actually the estimated versions of the noises. Understand what I'm saying? So the noises are, or basically the process generating the noises is not observable, guys. Okay, but let's say you have capital T of them. So you have a sample of size capital T, basically, which is given, but keep in mind, this is not necessarily equal to the sample size of, let's say, an AR process from which the noises are generated from. Okay, now this is the notation. Okay, and as I mentioned before, 1 by T is gone. So all you're left with is basically this expression, guys. Okay, and that's basically, you know, corresponding to the things that I mentioned before. So if you take that, this is the sum of the squares, by the way. So you can call it basically, this could be TSS. All right, so basically with TSS of the noises. Okay, so total sum of squares, right? And that's what I was mentioning. But there is no regression involved, including the noises. Keep in mind, guys, that most of the time noises are not observable unless you would simulate them yourself. Okay, so that's something that you should basically considering. Okay, now, and this is how it would look. Now, when it comes to residuals, okay, so now, first off, one property is that the mean of the noises is not necessarily zero. And that is something that I want you also to consider. The expectation of a random variable is not equal to its sample mean, guys. Okay, so that's not the case. All right, keep that in mind. This is something that I also see a lot of times in your notes, and I must penalize you for that when I see that, because that's wrong. Okay, so the expectation operator is applied on a random variable, whereas the sample mean is a sample mean, and these are two different things. You can argue that the sample mean is an estimator for the expectation of the corresponding random variable that is involved. But keep in mind, these are two different things. And so is the variance and the autocovariances. Understand what I'm saying? So most of the time I was looking at basically that from the theoretical perspective. This slide is actually from last week, is the first slide where I would basically consider, for example, sample autocovariances the way they are calculated from a sample. All right? Now, of course, we were doing simple linear regressions and all that stuff, but not in the context of time series. Okay, that was your job to basically to transfer those things into the context of, let's say, an AR or OLS regression for an AR process, both for the simple linear regression case as well as the multivariate case. Okay, so multivariate case, that was assignment 4, and univariate case, that was assignment 3. Okay, so the transfer was done basically by you. Okay, but these things were calculated differently, so keep that in mind, guys. This is something else. Now, anyway, okay, I would basically, and that's something that I want you to mention. This is different than the expectation of the random variable. So if I say mean, it could be the sample mean or the theoretical mean. You have to figure out from the context. If you see something like this, this is basically the sample mean of the noises. And let's say you would simulate a sample of the noises. It's actually never going to be, its mean is never going to be exactly 0, almost surely. You know the term almost surely, by the way. Okay? You understand what I'm saying, guys? So this is something that you need to be aware of. Okay? And I would, you know, remind you of that, especially when you consider, for example, your empirical work, because you need to distinguish between that. Now, when it comes to residuals, the sample of residuals, this is different because the mean of the residuals is equal to 0 if the regression from which the residuals were estimated from contains a constant. So if it has a constant, which it usually does because nobody basically drops the constant, but I mean, there are exceptions though, but if it has a constant, then it's going to be, the mean of that is going to be 0. Okay, so that is different. These are the estimated versions of the noises. So noises and residuals are not the same, and I want you to basically to be aware of that. Residuals, again, are the estimates of the noises, okay, but they're not necessarily equal. Now, you could calculate basically the empirical covariances, but the issue is that the means are going to be 0, so you're just going to have, and if you basically adjust the formula, you're just going to have the product of the corresponding processes or observations that are involved in the numerator divided by basically the square of the the sum of the squares of the observations. This is going to be the residual sum of squares then. You understand? So this is basically what it would be. And this is how it's calculated. So when it comes up, this is how it's done. All right? And these are two different expressions because one is referring to the corresponding process and the corresponding observations, okay, that are not observable in general. And one is going to be based on the corresponding estimators, which are, again, estimated. They're not observed directly, but they are estimated. I mean, they are calculated from observations, you know, but they are estimated. Okay, so they are not necessary. Okay, so basically, again, that is also important. Since this is not observable, it's clear that basically the corresponding noise at time point t is not equal to its estimate in general. Okay, so that should be clear. Okay. All right, and so neither is the sample mean and the sample variance and the sample autocovariance. Anyways, okay, now I want to talk about basic properties of these things. The first property is that within the univariate case, when it comes to the noises, the sample autocovariance, okay, converges in distribution to the standard normal distribution if it's multiplied by the square root of the sample size as the sample size basically progresses. So as the sample size progresses, okay, the test statistic, let's call it this test statistic here, it has no specific name, would converge to the standard normal distribution. It doesn't necessarily mean that it is normally distributed, but again, keep in mind, this is convergence in distribution, okay? We talked about that concept, all right, when it comes to basically the CDS, the cumulative distribution functions of those things, of the sums. But when it comes to correlations, you need to understand that sums are involved, okay? So there is some sort of an arithmetic mean that is involved in here, okay? And since, I mean, if these noises are independent, which they are assumed to be, then they would, you know, satisfy the central limit theorem of some sort. Anyways, so that's basically what it's going to be. So this is not difficult to show, but I'm going to basically skip that part, okay? And then within the multivariate case, since noises are serially uncorrelated, and that's basically reflected here by this expression. Keep in mind, guys, this is an H by H identity, so this is an identity matrix. You know what an identity matrix is. It has H rows and H columns, okay? So you have basically ones on the main diagonal and zeros elsewhere, and that should be basically understandable here, okay? So, and this is an H by H identity matrix, and that is going to be the variance covariance matrix of this expression, okay? And since it's going to be standard normal, this is the multivariate standard normal distribution. All you would need to know is, since basically the noises are uncorrelated, that means that basically their theoretical autocovariances are going to be 0. Keep in mind, guys, that this thing would converge in distribution, but it doesn't necessarily mean that the empirical autocovariances are going to be 0 until then. You understand what I'm saying? So that's something that you need to be basically aware of, okay? But since, you know, noises are uncorrelated, and that means serially uncorrelated, you know, you have basically within the multivariate case an H by H identity, indicating that the autocovariances are going to be 0, let's say in the long run, all right? So that's basically what it would be. All right, guys. Now, I'm going to construct test statistics based on that, okay? So I will take those and we will develop some sort of hypothesis testing, okay? So the hypotheses, and then based on the normal distribution, which you can do, is going to be, the null hypothesis is going to be that the autocorrelation at a specific time lag, okay? So which I'm going to refer to as time lag H, is going to be 0. So that's basically what the null hypothesis is. Keep in mind, this is the theoretical autocorrelation, not the empirical one. So if I write it like this is going to be the theoretical one, and if I write it like this, okay, then it's going to be the empirical autocorrelation, okay? The null hypothesis is always making a statement with respect to a parameter which is always coming from a statistical population, guys. So this is a quantity of a statistical population, so always going to be theoretical. Okay, keep that in mind, so don't confuse that. I have basically the impression that people do not distinguish between empirical and theoretical expressions, all right, which I want you to, so I would like you to basically to be aware of that. Now, the alternative hypothesis is just a negation of that. This is a two-sided test, and I'm going to basically apply this within the context of the standard normal distribution, okay? So, of course, the test statistic that I'm considering is the square root of the sample size times the corresponding empirical autocorrelation. So keep in mind, this is not equal to its theoretical counterpart. You should understand that, right? So that's different. But you should calculate this autocorrelation. Now, I was basically telling you how to. So that was on the previous slide. And if you basically, you compare that to the standard normal distribution, you should reject the null hypothesis if and only if the absolute value of the test statistic is greater than the 1 minus alpha half quanta of the standard normal distribution. So this is basically how it's working, okay? I would basically add that, don't confuse this, this does not follow, okay, the standard normal distribution, although we use the quantiles of the standard normal distribution as a base. But this is asymptotically going to be standard normal. So this is just converging to the standard normal distribution as the sample size basically increases, so as the sequence progresses. So this distribution is not exact, okay? I would argue that you should have at least 30 to 40 observations minimum, okay? Effective number of observations minimum to be able to perform a test sufficiently basically based on the standard normal distribution. But some people do argue that you need more. Okay, so after, let's say, 50 observations, you know, so that would be fine. Okay, I'm not going to. So basically, I'm going to violate that rule of thumb because I would only have 5 observations. And of course, you would not, you know, it's not appropriate, let's say, to apply a test like this on a sample of size 5 based on the standard normal distribution, only asymptotically, guys. So the test statistic, and again, keep in mind, only asymptotically follows the standard normal distribution, but I did it anyway. Okay, so because I wanted to illustrate how it's done, and you could do that also. So if you want to apply this, you can. Okay, now I'm going to test the null hypothesis that the first order autocorrelation is going to be 0. And I would calculate basically the mean and the variance of the sample before that. You can do that. You can verify that statement if you like to. So again, you're welcome to do so, but you don't have to, of course. Okay, the empirical mean, okay, the sample mean is the sum of the observations divided by the sample size. The sample size is, of course, 5, so this is going to be the mean. As you see, it's not 0. Okay, these are not residuals, guys. Let's assume that these are basically sample observations of noises of some sort. I was simulating them, actually, based on the normal distribution, but anyway. Okay, and the empirical variance, again, mean of the squares minus the square of the mean, the uncorrected version. The empirical variance, okay, not the theoretical one, is or was actually, okay, 0.6622. This is the mean of the square deviations. So that's the uncorrected variance, not the corrected one with degrees of freedom. The uncorrected one, because this is something that I need for regression. All right. Now I would calculate the autocovariance too, and the autocovariance, okay, is calculated based on with respect to the time lag 1. So you have 4 observations, okay, at the beginning. So this is going to be the first 4, okay, and then 4 observations at the end. So you're going to have 4 observation pairs, okay, that one with that one, and then you will have basically that one with that one. Okay, which is involved, so then you have that one with that one, and this is the third, and this is the fourth. Although we have 4 observation pairs that we use basically to calculate the autocovariance, we divide the sum by 5. So keep that in mind according to the formula, because capital T is equal to 5. Okay, so that's something that you need to be aware of. Okay, so then of course, you know, accordingly, when you calculate the autocorrelation, 1 by 5 will cancel out anyway. Okay, but if you just evaluating this thing, you would need to understand this. So this is going to be negative, right? That's something that you would need to understand here. I was using the mean here. Okay, so you have each observation, so that observation minus the mean, okay, times that observation minus the mean, okay, and that would be the first pair. And then this is how you go on, all right? So, and then you have 4 pairs, 4 observation pairs, but you divide basically the sum by 5, not by 4, by 5, all right? So this is how I did it. Then you simply calculate the autocorrelation by dividing the 2, and that's simple. Okay, again, 1 by 5 would cancel out. And this is what I got, so negative 0.5 approximately. Of course, these are not exact values. Okay, these are just approximations, of course. Okay, but I could not display them because that was too large. But you could do that if you want to know what this is. You should do that yourself. Now, for the test statistic, it's simple. You take the autocorrelation, which is here, and multiply it by the square root of 5. Okay, so take that, multiply it by the square root of 5, and this will yield the test statistic. That's simple. Okay, now this is what it's going to be, and if I did it correctly, this is going to be negative 1.17 approximately, 1.18. That's going to be the test statistic. Now, what you're supposed to do, you're supposed to reject the null hypothesis if the absolute value of the test statistic, at level alpha, of course, if the absolute value of the test statistic is greater than 1 minus alpha half quantile. So I'm talking about basically if I use the error probability of 5%, which I usually do as a default value, then I'm looking for the 1 minus alpha half quantile, which is 1 minus 0.05 by 2. I mean, when it comes to basically the index of that, and this is going to be 97.5. So I'm looking for the 97.5 quantile. Why I'm looking for the 97.5 quantile, not the 95% quantile? Because I'm going to cut off 2.5% of the distribution on the right and 2.5% on the distribution of the left to get basically the 95% range for the test statistic, which is going to be the acceptance range then. Keep in mind, guys, this is a two-sided test. Okay, so since it's a two-sided test, you cut off like literally 2.5% on the right and 2.5% on the left, and you need to have the 97.5% quantile for that. You understand what I'm saying? So that's going to be basically the acceptance range. Now, how to? Okay, so how would you find that? It's simple. Okay, so you have seen this distribution tables already, okay, which is 1.96. So 1.96 is a 97.5% quantile. So if the absolute value of the test statistic is greater than 1.96, which is called the critical value, so the critical value is establishing the acceptance range for the test statistic as well as the rejection range, okay? And since we are basically inside the acceptance range because the test statistic is between negative 1.96 and 1.96, we do not project the null hypothesis. So statistically speaking, there is no first order autocorrelation within this sample, but keep in mind, guys, the sample observation, the sample observations, or the sample size, sorry, is relatively low. Okay, so again, usually nobody would do anything like this, but I wanted to basically to demonstrate how it's done so you understand the application. Yeah, you raise your hand, sir.
There's no autocorrelation.
From the statistical point of view, yes, from the empirical, or you can say from the empirical perspective. Although the autocovariance or the autocorrelation of, let's say, 0.5, or let's say its absolute value appears to be relatively large, but the sample size, okay, is relatively small. So in case of 5 observations, there is a lot of things that need to happen to have a significant autocorrelation. You understand what I'm saying, guys? Again, but nobody does that based on the standard normal distribution, but the problem is, what am I supposed to do then? Okay, what were I supposed to do otherwise? Okay, so these tests are not, or basically the distribution of the test statistic under the null hypothesis is not going to be exactly the standard normal distribution. That's a problem. Okay, so these tests have different qualities regarding their applications. Okay, So there might be somebody else who would argue, okay, don't use this test statistic, use another one because it has a better conversion rate, whatever. Okay, that's not what I'm going to be focusing on here. You understand, guys? Okay, so that's something that, again, I'm just basically want to try to illustrate. And I'm going to repeat that stuff for the second order autocorrelation. So I'm going to test basically the null hypothesis for the second order autocorrelation. The only things that, I mean, the empirical mean and the variance don't change, of course, okay? But so does the autocovariance and the autocorrelation, almost surely, let's say, which is going to be the case. But keep in mind, guys, for the autocovariance, you only have 3 observation pairs because the lag order is 2, okay? So you basically take that one, and with that one, then you take that one and that one, okay? Then you move on, and that one with that one, and that's it. Okay, so these are the 3 pairs. Okay, second order autocovariance. But you need to understand this is going to be divided by 5, not by 4, and not by 3, as it was the case for the simple linear regression. Okay, because I was asking you how many observations the predictor and the response would have, but there is no simple linear regression involved in here. Okay, so there was always the effective number of observation pairs is 3, although the time series has 5 observations. You understand what I'm saying, guys? Okay, so there is just 3 observation pairs that are involved. Anyway, so I was basically calculating those expressions, so the empirical autocovariance, and simply just take that and divide it by basically by the empirical variance. Now this tends to be less. Okay, so again, autocorrelations tend to be basically decreasing, okay, as the time lag, I mean, the absolute values, guys, as the time lag increases, but that's not always the case though, right? This is just a tendency. Anyway, so you would not reject the null hypothesis either. I mean, for the first case where you would consider the first order autocorrelation, and we had an autocorrelation of negative 0.5 or something, we didn't reject the null hypothesis, but we are going, I mean, we're not going to reject it for that one either, but I was calculating this anyway. So the test statistic is simply just the autocorrelation multiplied by the square root of the sample size, and that's going to be the test statistic. All right, that's not actually not that difficult. Keep in mind, guys, these are approximations, okay, which are not subject to approximation error, because I was not using them. So this is not the value that I used. I was leaving that value to calculate statistically for the computer. Now the test statistic is even lower, but again, the critical value is the same. It's the same distribution, all right? So same underlying distribution, of course. And since basically the absolute value of the test statistic is not greater than the critical value, then we don't reject the null hypothesis. So that's basically the same issue, all right? It's not going to be rejected either. So there is no autocorrelation from the empirical perspective, at least not at the 5% level. So you can, if you basically, you know, you're doing things like this, okay, within a thesis or whatever, you can simply write there is no autocorrelation at the 5% level for the lag order 2, something like that, or from the empirical perspective or whatever, okay? But you should also mention the error probability that you're using as a reference, okay, because that's, you know, basically requires, if you want your statement to be falsifiable, okay? You understand that, guys? So again, there was no error autocorrelation. If it were, I mean, that would be suspicious regarding noises, because noises are uncorrelated from the, basically from the theoretical perspective, but it could happen that, you know, randomly speaking, there is some empirical autocorrelation which might be significant still, okay? But that would be just a coincidence if there were real noises. Anyway, so that would contradict basically, if you ever had autocorrelation, that would contradict the basic property of noises, by the way. But again, that's something that I don't want to get. All right, now, I'm not sure whether you know what the definition of the chi-square distribution is. Based on that, I'm going to develop other test statistics as well. But let me recall this. So the chi-square distribution is actually a distribution of a sum, and this sum involves squares of standard normal random variables. So the z's are following the standard normal distribution, and they are independent. And the number of those is referring to the degrees of freedom that the distribution has. So again, I'm not sure if you've seen this. Usually in an undergraduate class, I teach that one. But there are, I mean, my experience is that there are basically lecturers who don't explain this in detail. Okay, now if you don't explain it in detail, basically how would students expect to understand the chi-square distribution anyway? But that's something that I don't want to discuss. Okay, so this is the notation here, guys. Okay, so y would follow the chi-square distribution if it's equal to a sum of squared standard normal distribution or random variables. Okay, so sum of squared independent standard normal random variables would generate the chi-square distribution. So whenever basically a square of a standard normal variable is involved, whenever the chi-square distribution, I mean, in the sum of those involved, then it's going to be basically that. Now, I just wanted to mention here that, for example, if let's say z follows the normal distribution, the standard normal distribution in particular, then this implies that its square would follow the chi-square distribution with exactly 1 degrees of freedom, because you only have one summand, right, involved. Okay, so the square of a standard normal variable would follow the chi-square distribution with 1 degrees of freedom, or 1 degree of freedom. All right, is it understandable, guys? Okay, and if you have a sum of those, then it's basically equal to the number of summands that you are considering. Okay, and based on that, I will develop test statistics that follow, at least asymptotically, the chi-square distribution. And you can do that basically when you have asymptotic standard normal distributions. Okay, so just for the moment, the standard normal distribution was looking like that. And if you take the same basically random variable, but you would square it. Okay, so you would take the square of the test statistic. This test statistic would asymptotically be following the chi-square distribution with 1 degrees of freedom. Okay, obviously. So again, because the square of a standard normal random variable would follow the chi-square distribution with 1 degrees of freedom. All right, guys, is it clear? Okay, so that's exactly what this slide would argue. And yeah, so you could use basically the chi-square distribution instead, but nobody would. I mean, why would you? All right, so you simply just take the square of that test statistic. Now, the square of this expression is, of course, t times the square of the empirical correlation, right? I mean, I think you would see that. And then this would generate also another test statistic when you sum up these things. Okay, so when you take those, okay, and you sum it up with respect to age until, let's say, m or so, then you could jointly test the autocorrelation. Okay, so that would be basically generating some sort of f-test based on that, but you can use the chi-square distribution for that. So you would have basically the sum of these chi-square distributed random variables would generate also a chi-square distribution. So the sum of the chi-square distribution is going to be the chi-square distribution itself. Okay, so let's say if x follows the chi-square distribution with 1 degrees of freedom, and y would follow the chi-square distribution also with 1 degrees of freedom, and x and y are independent, then of sum would follow the chi-square distribution with 2 degrees of freedom, obviously. Okay, so this is basically the fact that you see here, okay, because I got m summands here, so that would be following the chi-square distribution with m degrees of freedom, because there are m summands involved in this sum, each following the chi-square distribution with 1 degrees of freedom. And we assume that these things are going to be independent. All right? Now, again, this is just asymptotically true. Okay? So as basically the sample size would increase. Only asymptotically, but not exactly. So there might be people, arguing about the convergence rate, which could be relevant, and depending on the process where the noises are, or let's say estimated from. Keep in mind that this is only true for noises, not necessary for residuals, but people apply this for residuals anyway. So again, I mean, what are you supposed to do then? Okay, so you would not basically apply maybe one test or so, but if your results are contradicting or inconsistent, you would apply basically 2 or 3 tests for autocorrelation. So that This is designed for noises, not for residuals. But again, what it's supposed to do. Anyways, okay, so I was giving you the reference, okay, of box pairs in the original slides, but don't display it here on the presentation. And again, I take that, okay, for the test statistic and testing the joint hypothesis that the autocorrelations of the first and until order, basically each of them is going to be 0. Now, again, I'm going to apply this later on, okay? So you'll see how it's done. The alternative is simply just a negation of the null hypothesis. So this means that there is at least one autocorrelation which is not 0. Which one? You don't know, okay? So that's a disadvantage, but you can jointly test that, okay? So you can jointly test the hypothesis that there is no autocorrelation in the data. Okay, all right, but if you reject the null hypothesis, you don't know from this test which autocorrelations, maybe there are more, were responsible for that, at least from the empirical perspective. All right, guys, now you take that, okay, so you're going to calculate this test statistic, which I refer to as BP. This is the sum of the squared, I mean, you know, this thing, okay, so inside would follow that one. This test statistic would follow asymptotically, at least, the standard normal distribution. All right. So the summance would follow asymptotically the chi-square distribution with 1 degree of freedom, and then the test statistic itself would follow the chi-square distribution with m degrees of freedom. That should be obvious. All right. By the way, if you understand the definition of the chi-square distribution, you should reject the null hypothesis at error probability of 5%, if and only if the test statistic, which its absolute value is never negative, of course, okay, sum of squared numbers cannot be negative, is greater than the 1 minus alpha quantile of the chi-square distribution with m degrees of freedom. So now you see the explanation, basically what it is, okay? So that is the 1 minus alpha quantile, not the 1 minus alpha half quantile, guys. This is a one-sided test, not a two-sided test. Then either all autocorrelations are 0 or not. All right, so there is just basically these two options. This is a one-sided test, so you cut off basically 5%. So if you test this at the 5% level, you 5% basically on the right of the distribution. Okay, because the greater the autocorrelations are with respect to their absolute values, the more likely you would reject the null hypothesis because the greater the test statistic becomes. Okay, now I'm going to test this. For this sample, yeah, you got a question, yeah.
So, in order to verify the autocorrelation analysis, we either test the standard number distribution, I mean, this first test that we did.
Yeah. You could do that with the chi-square distribution too, but you would need to square it. Well, why would you, right?
For every single lag separately, or we do the box pairs.
Yes, exactly. Or you do both. So either you do separately, yeah, sure. I mean, either you do it separately. I mean, it depends what you want to basically figure out. You know, maybe you want to know which autocorrelation was responsible, you know, for rejecting the null hypothesis of the box-Pierce test. So if you reject that, I would start with that one, actually. And then I would, you know, if I reject the null hypothesis, then I would look maybe into, you know, which autocorrelation was responsible for that, because that might have a reason, okay, when it comes to the structure of the data. You understand what I'm saying? So let's say it's this autocorrelation with respect to time lag 4 or something, that it could be it could indicate that you will, if you have an AR process from which you would take these residuals from, that you might include basically a additional explanatory variable until you would eliminate autocorrelation, because the problem is there is omitted variable bias, one of them. So if residuals are autocorrelated, then it can be shown that, for example, the estimates of an AR process are going to be biased. Okay.
So when we have this autocorrelation, we somehow try to re-estimate the. Sure,
you would reselect. I mean, you would let's say you would reconsider your model at that point, because if noises exhibit autocorrelation, which they're not noises then, right? No. So then, of course, you can solve this issue by adding additional explanatory variables into the model, okay?
Or decreasing the number.
Excuse me?
Or decreasing the number of variables as well.
You would increase the number of explanatory variables, right? Increase. You would put in more.
Decrease, no?
No, I mean, why? So if basically residuals, okay, exhibit autocorrelation, let's say at the 5% level, because you reject, let's say, the null hypothesis of the box Peirce, you know, this means that empirical perspective, then the estimates are going to be biased.
Yeah,
so you need to have more exponential variables to eliminate that.
Yeah, but maybe the model is overestimated. I mean,
if it's already overestimated, then the model might be misspecified from the beginning. So you might have a different model class that is involved. You know. So maybe I come back to this point after a while. So I mean, I was addressing that, but how to? So there is two approaches basically to address that issue. One is, top to bottom, and the other one is from general to specific. Top to bottom from bottom to top means that you add exponential variables until autocorrelation of the noises is eliminated from the empirical perspective. You need to eliminate those. So that's the first thing that you do, by the way. So when it comes to a regression model in time series, always, and I mean always, test basically the noises or residuals to be honest, on autocorrelation.
So first we increase the number of variables.
You need to, this might indicate again. So the problem is that you're talking about is that nobody knows what the true model would be.
Yeah.
How would you know that, right? So I take that as an indication that your model is too small. Now, if you basically have already a model which is overfitted in this regard, then I would choose a different model instead. For example, if you have an AR processor, you would try to make it bigger, but if maybe it's too big, as you mentioned, then you would consider an ARMA model instead, because that might capture the dynamics better than the relatively large model. All right, so that could be also an answer to your approach, but it depends on the model that you are considering. Yes.
What's the general practice when we have this autocorrelation?
There is none. There is none. It depends. This is, like walking in the dark. Where would you go? Nobody knows, right? So, but you could justify that. So, if I see you have autocorrelations the residuals exhibit autocorrelations. Okay, I take that as an indicator that you need to have more exponential variables. Now, which one? That's a question. Okay, but if the model becomes too large, there is, let's say, an AR process, you would try to establish an AR model, and this becomes too large, you might consider an ARMA model instead. This is what I try to basically give you as a next assignment. So I'm going to give you a new sample. I would like you to ask you to establish either an AR or an ARMA model involved basically for that. Why would you use an ARMA model maybe? You could justify that because the corresponding AR model turns out to be large. Okay, and it still has autocorrelation, so it might be not basically would be a good one. So then you would justify your ARMA approach by that. You understand what I'm saying? So it's not about basically what model you're selecting. It's more like how you're justifying it. That is very interesting, at least to me. You understand?
Maybe, for example, solve this issue by subclassification as well?
Yeah, exactly. Yeah, so this is going to be your next assignment, by the way. Okay, I'm not. I try to evaluate assignment 4. That's what I'm trying to. But maybe I can do it today. Hopefully, then tomorrow assignment 5, and then I would be finishing this by the end of the week, hopefully. But you have at least 2 more left. You understand? So I want you to experiment. Okay, and yeah. Again, there is no general approach regarding this. So there are multiple indicators. I'm going to introduce you to them. Okay, but that's one. So try to, again, my approach is try to eliminate autocorrelation for residuals. That's because then you know if there is one, let's say, and that the null hypothesis would be basically false. And you would say that by about 100% degree. Of course, you cannot, because you don't know which process was generating the observations that you have. Okay, so it's always, you know, a question. But let's say the alternative hypothesis is true, which means that the noises do have autocorrelation. Then they are not noises, right? That's number one. And number two, then the estimators that you'll have are going to be biased then. This is called omitted variable bias, by the way. This is a phenomena. I think, you know, some of you guys have basically discussed this in statistics too. Okay, so or maybe you do it in Econometrics. I cannot do that, but there is a proof. It's a very simple one, that if you omit exponential variables that are significant or that are relevant, let's say, not talking about their significance, if they're relevant, that the estimations are going to be biased. So try to eliminate autocorrelations within the noise. Okay, that's something actually you have to. Okay, so that's always, whenever you implement a specific model, that's something that you should do, by the way. Okay, and if there is no autocorrelation and you can justify basically the model, then nobody's going to criticize you for that. But maybe you cannot do that, so then you could argue that it's not possible. Okay, then the process behaves differently, whatever it would be. All right. Anyways, yeah, so this is basically how it would be. Okay, sample observation is 5. I'm going to test this hypothesis jointly. Of course, I was not rejecting it individually, so that might indicate that I don't reject this hypothesis either, but it could be the case that I do. Okay, so sometimes these results are not consistent. Okay, you might not be able to identify, I mean, these correlations, okay, with respect to time lag 1 and with respect to time lag 2 were relatively small, but if you put them together, maybe they could add up to something, right? Again, so it's not always consistent. Okay, so just because you don't reject the null hypothesis for test A, it doesn't necessarily mean that you would not reject it for test B either, although it partially is involved. All right, but again, I was testing it. So I would calculate basically autocorrelations, which I was using here in the previous part. I'm not sure about that one, by the way, but again, I will come back to that later on. And this is the test statistic. If you take those, okay, so you would take each of them is multiplied by the square root of 5, and then you would square those, okay, and then you would sum them up. So that's basically what it is. All right, or you square them first, okay, which you can do also, and then multiply it by 5 later. Okay, so you square them first, okay, then you add them up, and then you multiply them by 5, and then this would be the test statistic. All right, now that doesn't reach basically the quantiles of the normal distribution. Error probability is of course 5%, which I use here, so I test this at the 5% level. Then I would need the 95% quantile, because 1 minus 5% is 95%, so you have the 95% quantile of the chi-square distribution with 2 degrees of freedom. Why 2 degrees of freedom? Because it has 2 summands, simple, all right? So this is the 95% that you're looking for. There is a distribution table that you basically probably aware of. The F means degrees of freedom, so these are basically your rows, and in the columns you have basically 0.95, which stands for the 95% quantile. So these are the 95% quantiles of the distribution, and of course you'll find that this is 5.99, approximately 6. So let's take 6, all right? So this is going to be, the critical value is going to be 6, and we are not even close. So 1.57 does not reach that. So the test statistic is not large enough. So if I did it correctly, guys, which I hope I did, so maybe you can correct me on that, all right? I'm not sure about these correlations anymore, but maybe you can check it out. You don't reject the null hypothesis, by the way, in this case. Okay, so neither the box-Pierre test nor these individual tests are basically coming to the conclusion that there is autocorrelation involved. Again, but keep in mind, guys, that the sample size here is very small. So it's not a good asymptotic, by the way. So it needs to happen. You know, there is a lot of things that need to happen for a small sample like this. But I wanted to have an application attached to it, guys, that you can basically re-evaluate. So you might be falsifying my results that I'm producing here. Okay, now this is the box-Pierce test. Okay, again, these are just asymptotically, this is just asymptotically true, so keep that in mind, please. And you need to understand that there is also an alternative. Okay, it's based on the box-Pierce test, so that's basically the starting point. If you look at that, this is exactly the same thing as here, okay, but it's a modified version because it has shown, at least by simulations regarding the studies, that the alternative is a little bit better. Now, the question would be when to choose basically the first one and when to choose the alternative. Again, so these are attached to you. The autocorrelations have different weights. This is the approach. Okay, so they have different weights. Okay, and the further they basically, I mean, as h increases, the denominator would decrease. So autocorrelations with a the reason for that is, let me tell you something. Okay, when it comes to autocorrelations, the autocovariance has t minus h observations. So that's the point. All right. So the greater the time lag would be, okay, the less the number of observations that are involved is going to be. Okay. So this means that since it has fewer observations, as the time lag would increase, the estimation has a greater variance. Okay. Now, since it has a greater variance, that is considered to be more relevant in this case, because if I divide it by t minus h, then okay, then it has a greater weight. So autocorrelations with basically with greater time lag, okay, would also have a greater weight regarding the sum. So just basically rearranging the sum, and I would add basically new weights to the sum. Okay, now this had been shown that when it comes to simulations, okay, so simulating data, that the Ljung-Box test performs better. But it could be the case that for a different class of models, it doesn't do that. Okay, so the question would be, I mean, nobody knows this because from the theoretical perspective, it's very difficult to illustrate that. So that was basically just a suggestion. It turned out to be true. Okay, but from the theoretical perspective, it's very relatively difficult for which model you would do that, because the issue is, guys, these are just these things are only asymptotically true. So the test statistic is not directly following the chi-square distribution, only asymptotically. Okay, and it could be that, for example, this alternative performs within a certain circumstance better than this one, which from the empirical perspective, it turned out to be the case. But it could be that you have a different class of models for which you would use the former. Now, which one you would use? Probably both. Okay, but I would basically, most people would consider that one first, but this was developed based on that. So that was basically the base for that. Okay, I was doing both. Okay, so let's see what happens. Basically, so again, this is the procedure. The null hypothesis is the same, the alternative hypothesis is the same, and the critical value is the same, although the test statistic is just different. Okay, so it's all based on the chi-square distribution with the same degrees of freedom, but the noises basically are different. Now, I will use basically the same thing that I used basically before. Okay, so these were the autocorrelations, and the Ljung-Box test statistic, as you see, is greater than the previous one. And that tends to be the case. Okay, so it's more sensitive, let's say. Okay, so when you first, let's say you would do the box-Pierce test first, and then you come close to the rejection range, I would basically definitely consider the Ljung-Box test also. Okay, and the reason for that is, of course, because this autocorrelation, okay, since it's based on fewer sample observations to calculate it from, with fewer observation pairs, let's say, when it comes to the autocovariance, of course, you know, it has a much greater weight. Okay, so it might be basically because it has a greater variance, so it's just basically affected by it. Now, the error probability is 5%, and the critical value is the same. That was 6 approximately, so just as in the previous case. So, but you would still not reject the null hypothesis, so this is still not enough, but I would at least come closer to the rejection range. Understand that, guys? So it could have been the case, but it wasn't. Anyways, okay, so that's that. All right, so, but I need to basically repeat that one. So this is only true for noises. However, when it comes to residuals, this convergence is not true in general. Okay, so that's something that you need to know this. So the application of these tests, okay, for residuals at least, is, let's say, not very straightforward. People do it anyway. Okay, so they apply the Ljung-Box test anyway, because again, the major issue is that, you know, nobody has these noises in general, so we need to estimate them, right? But again, I mean, what am I supposed to do, actually? So, but there is an alternative, but this has a price. There is a price to pay, okay? So, and this is basically, I mean, the way to come out is done by the Breusch-Godfrey test, which is, you know, used for residuals, okay? Now, when it comes to residuals, you need to have a model that you're estimating, because that's always based on a model, okay? So you would take the residuals from your regression model, okay? So let's say, I mean, I will give you examples. So that's the first step. You need to have the residuals estimated, okay? Residuals are always going to be, if you want to estimate the residuals, this is going to be a response minus the fitted values, always, no matter what, always. Okay, so whatever regression you have, it doesn't matter. Okay, so it's always going to be your responses, your observations of your responses minus your observations for the fitted values that would generate the residuals, depending on the model. Okay, if it's an AR model, then you would need to estimate that. If an normal model, that you would need to estimate that. It doesn't really matter what kind of model you use, so you can use any model. That's a good one, any one. Okay, now, so I would write it like this. Okay, so there is predictors. I mean, actually, it's not predictors. It's the linear combination of predictors, right? Because you have, you know, some constants involved. So it's not just predictors. There I have the coefficients, okay? Predictors and coefficients, okay? So that would generate the linear combination. But I was saying just predictors, that for simplification, but it's not precise, to be honest, okay? So you would need to find the residuals first, again, and you would simply just take the observations minus your fitted values. Now, if the fitted values are given like this, so Z's are the predictors, okay? These Z's are predictors. It can be an AR process, so let's say you have an AR process, then the first order autoregressive one, okay, so let's say you have a first order autoregressive one, then Z is, okay, so the Z prime is the transposition, okay, so there is a constant involved, and then there is the first time lag, which is Y, okay, so this is basically the generalized version of the predictor. So keep in mind, guys, that Z's are the predictors, and since you multiply it by a vector, this would be a linear combination of the predictors, okay? All right, so I will give you examples for that so you can check for yourself, okay? So these are your fitted values, right? Of course, okay? And since already you have an estimation, these are your estimates, of course. Good. Now, let's say you have an ARDI model, okay, where you would have an autoregressive component as well as basically you have another, let's say another predictor involved, okay, for another variable, okay. So this is a distributed lag version, and then you have the noise, okay. So this is basically the linear combination of the predictors, right? All of them are predictors, including the constant, by the way. So I would consider that one as well, okay. So again, this vector includes the constant, okay. And then, of course, the estimates for the AR part and the estimates of the distributed lag part. So the number of parameters, okay, that are involved is going to be 1 plus P plus N in this regard. You understand what I'm saying? These are the number of parameters. P for the autoregressive part, N for the moving average part, and 1 for the constant. Is it clear, guys? So then if the time series, let's say it has T observations, the effective number of observations is going to be T minus 1 minus P minus N. This is the effective number of observations of an ARDI model. You understand what I'm saying? And that will be basically the number of observations of the residuals too. Because you have only this much. You understand what I'm saying? So that's basically important, guys. You learn this through your assignments. I hope at least, you know. Okay? Now, anyways, I read the term effective number of observations, and which I liked. Okay, unfortunately, I wasn't aware of that. But anyways, now these are the predictors. Okay, this is a transposition sign, by the way. Okay, just to remind you, okay, so A prime is going to be A transpose. But since I use capital T for the number of observations of a time series, I'm not supposed to use a transposition sign as well. Okay, I would use A prime for that. Okay, so theta prime is basically a row vector, which you see here. And the Z prime is also a row vector that you see here. It's easier for me to display it. Okay, now this is how you would have an ARDM model involved. And the number of residuals, again, in this sample is going to be capital T minus 1 minus P minus N if basically Y consider of sample size capital T. So you have, let's say, capital T observations of the process. You understand what I'm saying? So that is going to be the number of residuals that you'll have. But anyway, okay, so then, yeah, what are basically the, what do you do with that? That's, okay, so as soon as, you know, within the first step, you get the residuals, okay? What are you supposed to do with that? You take those and you estimate a new model, and the new model is going to look as follows. So this involves an autoregression, okay, of the residuals, including basically the predictors of the previous model. So Z is basically the vector of predictors of the previous one, okay? And then you put that into a new regression when it comes to the autoregression of that one, okay? So this is an autoregressive process with respect to the residuals, by the way. So you can say this is an ARDM model for the noise as an explanatory variable, where you would also include the predictors as well. So you have the predictors of the previous model inside as well. You re-estimate that, okay? And then, of course, you have, let's say, the noises of the noises, okay? So these are the residuals of that regression. And what you do after that is you calculate the coefficient determination for this one, okay? I mean, the software does that automatically for you. You understand what I'm saying? So since you, I mean, you can also argue how many observations you have. Now, if the time series Y would have capital T, then the effective number of observations of residuals is going to be capital T minus 1 minus P minus N. And since this is also an AR process of order M, you know, which is also including basically these predictors, that's already there, you know, so you re-estimate it. Minus M would be basically the total number of observations here for this noise, all right? But this is becoming a little bit too weird after that. Anyways, so these are the parameters that are involved, and you have new ones, these betas. Now, you test the null hypothesis after that, because you need to calculate the coefficient determination. You test the null hypothesis that these betas are 0. If these betas are 0, okay, what does that mean? Yeah, this means that the residuals have no autocorrelation, literally meaning. Okay, so that's basically what you do. And the alternative is, of course, it's negation. So at least there is one coefficient which is not 0, because if there is one, then there is autocorrelation in the data. That's the empirical perspective. And if the null hypothesis is true, then the effective sample size, so N is not the ARDM model. Unfortunately, I was running out of letters, okay, so this is not basically the order of the DL process, okay? This is a new one. I call this the effective number of observations, okay, for the auxiliary regression, okay? So the number of, basically, of errors or residuals here for that one. This is the effective number of observations for that. But again, it doesn't really matter. So, because if the sample size of the series would increase, that so does basically the effective sample size as well, okay? And if this is going to be asymptotically chi-squared as well, which is a good news, right? So based on the chi-square distribution, you can perform a test on that, but only asymptotically. Now, I wasn't doing that, by the way, because I would like you to ask you to do that, okay? So you would try to implement this, again, in your next assignment. And again, I will give you data, so you need to play with that a little bit, and you will need to document it in such a way that I understand your documentation. Okay, so that's going to be your major task, and you try to incorporate this in a little paper submission, okay? This is a big one, I understand, but that's how life is, okay? So I'll give you data, and then you play with that, okay? And yeah, this is basically you would consider it, okay? So you can take the chi-square distribution based on that. There is already packages that you can use, so I'm not blaming you for anything. Okay, but yeah, try to find an appropriate model based on that. Okay, now, so I'm not going to do an example here. I would like you to do it yourself. Okay, regarding this approach. So maybe you can try to experiment with an AR process based on that one. Anyways, and after that, you reject the null hypothesis if the test statistic that is involved is greater than the 1 minus alpha quantile of the chi-square distribution with m degrees of freedom. Similar to the previous one, but keep in mind this is the number of parameters that are involved. You can use default settings if you like to. I don't really mind. Anyways, yeah, so the issues regarding model selection, which is not a clear point, okay? Because again, it's very difficult. I mean, nobody knows what the true model is, so, and nobody's going to tell you, right? So it's like walking in the dark. You don't know where you are, and neither do I. So I don't even pretend to, okay? Just some lecturers do pretend that they know. No, they don't. Okay, how? I mean, that's an issue. So the issue is, one of the issues that you talk about is overfitting, of course. You have too many of them, okay? If overfitting basically occurs, you tend to have multicollinearity. Now, multicollinearity means that there is correlation between the predictors. And this is an issue because if there is correlation between the predictors, then the OLS regression, the matrix is not invertible. So the design matrix, you know what design matrices are not invertible if they don't have full ranks. Okay? Now, the design matrix, of course, is a n by k matrix. Okay? So k is the number of predictors and n is the number of effective observations. So it must be the case that the rank, this is one of the implicit assumptions, that the rank of the design matrix is at least k. Is at least k, right? Sorry, like that. Okay, so that's basically that. If it's not, then, I mean, you might remember when it comes to OLS regression that x transpose times x to the power of -1 does not exist. And this was basically the guarantee for that. So if there is multicollinearity, which means that there is linear relationship between the predictors of some sort, then OLS estimation, for example, is not possible. Okay, so you have too many spices in your dish. Okay, but that's it. Anyways, so that's an issue. That could be an issue. And the other one is, of course, the variance tends to increase of the estimations. Okay, and then this means that you have poor predictive performance. Okay, because you have relatively large deviations. So if the variance is large, then deviations of predictions to observations tend to be large as well.
So when we have coefficient that has a very high p-value over 0.1, can we just simply exclude it? And
it's difficult to basically to see what kind of where you would how or indications that are involved in here. So it's difficult to tell because there are different cases though. But the standard error of regression is not supposed to be large, relatively speaking, you know.
Yeah, but when we, for example, yes, exclude the coefficients and the error, the error squared is high enough, can we? I mean, is it a good model?
Again, it's always a question of your perspective. So, what is a good model by definition? You know. But what does that mean, high enough? So again, so what are you supposed to be when you would consider that? It's difficult to answer. I mean, the issue is, I understand your point, but the question is difficult to answer. And sometimes, no matter what you do, you cannot explain your response, no matter how many predictors you try to incorporate, you know. So what you're supposed to do by then, nobody knows, right? Yeah.
So
yeah.
It's a practice.
Yeah, but again, so the problem is, there are cases, I mean, it could be the case that you try to, let's say, basically feed your model all the time without generating anything. So the question is what? You know, what to feed it with. I mean, again, it's difficult to answer. Right? But if, let's say, you don't reject the null hypothesis, you do reject the null hypothesis of the F-test, this could indicate that your, basically, the number of predictors is sufficient. But again, is it always the case? I'm not sure. You know, so I cannot give you, let's say, a guideline of, you know, okay, if this happens, then you're absolutely sure, you can be absolutely certain that your model does the right thing. I cannot do that, unfortunately. You always have indicators, right? So again, one is, of course, a relatively large coefficient determination. But that could be also very suspicious when it comes to spurious regressions also, right? Because that might indicate that the process is not stationary even, you know. Right? So again, it's something that I cannot answer with 100% certainty, unfortunately. I admit it, you know, so again, but nobody knows what the true model is. So as long as nobody knows what the correct answer is, how would you basically evaluate my statements that I'm making? Okay? But I try to basically just explain what the issues are with having a model which is relatively large. And there is also a problem if the model is too small. Because if the model is too small, then omitted variable bias occurs. Okay? So the parameters are going to be biased. And the explanatory power tends to be low. So let's say a low coefficient determination would indicate that the number of predictors is relatively small. But again, maybe there is no possibility to incorporate more predictors, which, I mean, for the data structure. You know, so it's a question which cannot be answered directly, as I would argue. Okay, good. Now I just wanted to mention this. General to specific, I mentioned this before. You start with the large model first, and then you throw out insignificant ones. Basically, that could be one approach. Okay, but you need to be careful because, you know, the residual is not supposed to exhibit autocorrelations. Okay, so I would not do this in case of, you know, residual. You would reject the null hypothesis of a Godfrey box PSS. You know, so I would not do that. Now, from the bottom to top, okay, there is a different approach. You start with a small model first because, to my estimation, a good model is always a simple one, right? But what is a good model, right? And then you throw in additional predictors until basically residuals no longer exhibit autocorrelation. And that could be another indication that if you were eliminating it, okay, then this might indicate that you have a good one. It's difficult sometimes to do so. So if you do your next assignment and you fail to do so because your residuals still exhibit autocorrelation no matter what you do, then just write that. You know, the model selection in this regard remains uncertain. because the residuals are not free of autocorrelation. Right? Okay, then, okay, that's fine. I mean, if this is your answer, then that's your answer. Okay, so I would not penalize you for that. Okay, how could I? It's not your fault, right? It's not your fault that the data is such that, you know, you would need to deal with. And there is also a third one, which might be more helpful regarding model selection, and these are information criteria. Now, these are some specific functions that you can use for selecting models, and I'm going to show you how. Okay, so that's going to be the next one. Now, there is two major ones. I mean, there are a lot of them, so maybe like at least 24 or so. Okay, so a lot of people use different information criteria. I'm going to introduce two of them. The first one is Akaike, and the second one is the Schwarz criterion. Okay, so the Akaike is a function. K is the number of parameters that are involved. Okay, so you're going to see that here. It's 2 times K, which is, again, K is a number of parameters, okay, that you would need to estimate. Coefficients, let's say. Okay, so if I say parameters, I mean coefficients in this case, because the variance of the noise is also a parameter, but that is excluded from the consideration. This is not a coefficient, this is a parameter also. But you can focus on coefficients, okay? So if I say parameters, I mean coefficients in this context. I'm not looking at specifically of the variance of the noise, for example, that you would try to also estimate. And then you have 2 times the log likelihood function, okay? Now this is just a function. And then you would select a model. So let's say K hat is the number of estimated parameters, the estimate of the number of estimated parameters, by just finding the argument that minimizes the Akaike information criterion with respect to K. So that would be your model selection. Okay, so you select the model that minimizes this information criterion. Okay, you need to make assumptions. If you want to have the log likelihood, you need to make assumptions about the noise. But most people will simply assume that they're normal. So if you assume that the noises are normal, you can calculate the log likelihood function relatively easily. The greater the log likelihood function is, the better for the model. Okay, and the greater number of parameter is, you're going to get penalized for that, because you might be basically an issue that the model becomes too large. Okay, you understand? So that's basically it. And there is also another one, which is the Schwarz, or the so-called Bayesian criterion. And the Bayesian criterion, which is also commonly expressed, is this function that you would try to minimize. A T star is the effective sample size of the model. So this is always referred to the sample size of the residual. So if you're not sure about that, just look how many residuals you have, because this is always equal to the effective sample size. Okay, that would also correspond to the number of responses that you have, minus basically 2 times the log likelihood. Now, why I'm introducing those, because the Akaike tends to estimate the greatest model. Okay, so I mean, let me just go further a little bit how to deal with those. And you should select basically the number of parameters based on the minimization of the corresponding information criteria with respect to the number of parameters. Okay, so this thing would suggest you how many, for example, how many lagged past versions, when you try to estimate an AR model, how many observations you would try to incorporate. Okay, and for the Schwarz criterion similarly. Now, why am I introducing those? Because the Akaike tends to estimate the largest model. Okay, so most of the time it's the largest model that you would have. And if you use the Schwarz criterion, this is going to be the smallest model. So I would not go beyond basically Akaike, but I would not go below the model, the number of parameters from the Schwarz criterion. That is the reason why, at least this is my impression, that is the reason why these 2 information criteria are the most common ones. Okay, so they are used quite frequently. Okay, and they're all displayed. So then you know how many, basically number of parameters you try to estimate. All right, is it clear? So these are the 2 that are most common. So usually it's not likely that you would need to go beyond Akaike. Okay, so whatever again, that could be basically the lag order when you try to estimate let's say an ARP model, okay? Okay, so the question is how to select P, okay? Now, Akaike could be providing you an answer for that because P, a number of lags that you incorporate, the lagged observations that you incorporate into the model is directly related to the number of parameters that are involved, right? That's true. So Akaike would tell you maybe, let's say, it's 5 or so, okay? So you would have basically, I mean, number of parameters involved, okay? You could argue with that. And the Schwarz criterion could be telling you that it is 2, okay? So this means that you don't go beyond 5 and you don't go below 2 then. But what the true answer is, again, nobody knows. So that could be an example. If the difference between the two is relatively large, okay? I mean, the question is, what does that mean? But again, if this is relatively large, then this might be an indication that the model is misspecified from, I mean, just by its structure, okay? But again, where to draw the line, nobody really knows, okay? So you can work with that also. Again, so what I would be interested in regarding your next assignment is how you justify your approach. You can check out basically how other people done that, okay? And the more you're capable, you appear to be more capable of to justifying your approach regarding model selection, the higher, I mean, the more content I'm going to be regarding it, okay? So keep in mind, there is no right or wrong with this answer, okay? All that matters is basically how you sell it, okay? And these are the things that you have. If you basically come to the conclusion that it's not clear, then this is also a result. So just because, you know, you find your results inconsistent regarding model selection, that you could basically argue, you come to the conclusion that the specification might be wrong, okay? But that's something that you need to sell, okay? So I want you to basically to sell the model, or trying to sell the model to me when you analyze these things. I mean, you need to play with that a little bit, okay? Is it clear, guys? Okay, and also you look it up if, you know, what other people have done regarding this, so. But that's the general approach. Again, but nobody knows where you're going to. Okay, and that's also, it can depend on the data structure, it can depend on a lot of things, sample size, time dependency of the parameters itself, you know, stochastic volatility, whatever. It's relatively difficult. Okay, why would you basically, you know, I mean, what are you supposed to do then? You know, that's the issue. Anyways, that's what I wanted to tell today. That was the topic of today. Are there any questions related to that? No? Okay, then see you tomorrow then. And tomorrow we're going to talk about autoregressive conditional heteroscedasticity. All right, guys. Thank you very much. Take care.